What's going on, everybody? This is Mr. Diamond, and these are the example problems for single replacement reactions. Now, in order to do this, you are going to need an activity series, and there is one of these posted online, and there's also physical copies that I'll have in class for you. Again, the way this works is we have our metals over here, and then we're only going to worry about halogens for our reactivity series. We'll have halogens over here. Lithium on our activity series is the highest activity, and gold on our activity series is the lowest reactivity. And the way this works is when you have a single replacement problem, you have to look at the elements involved and decide whether or not the swap is going to happen. More reactive elements will beat or replace lower reactivity elements, and we'll swap them out of the compound. The key idea you want to make sure is highest reactivity shouldn't be alone in a single replacement reaction. To use our dance metaphor, the higher you go up the list, the more attractive they are, and so they are definitely going to be in the relationship, and they will kick out someone who is less attractive or less reactive than them. So with that out of the way, that little bit of explanation, you're going to want this close by, and we're going to be doing some single replacement reactions. Now, how do you tell that they are single replacement reactions? Well, just like these last few times, we have a couple of things. These are actually quite possibly going to be one of the easiest ones for you to identify. Anytime you have single element and compound. Single element and compound, where the single element is not oxygen. So as long as the single element is not oxygen and it's attached to a compound or it's grouped with a compound, you have a single replacement. So I'm going to write that down. Single replacement is single plus compound, and the single is not oxygen. The thing we're going to look at, our last type of reaction involves oxygen by itself reacting with another type of compound. So anything that's by itself other than oxygen, and if it's plus something that is in a compound. Oh, sorry for that, everybody. It's been a long day. We know we have a single replacement reaction. So here we have Na plus FeCl3, single thing compound. That tells us it's a single replacement. Now, before we actually start anything, we have to check our reactivity series, and we have to find both of these elements. Now, to figure out which ones you care about, Na is a metal, which means we're going to be using the metals column of our activity series. And then we look, Cl is not in the metals column. We want to check the other metal, which should be the other first thing. In this case, that's Fe. So the first metal, sodium. Sodium is right here. It's right there on our table, or on our activity series. And Fe is iron. Iron is down here. What that means is that iron is less reactive than sodium, which means sodium is good enough, is reactive enough, is strong enough that the higher reactivity will not be alone. It will kick out the iron. So this is actually going to boot out the iron. And if that happens, you're going to end up with Fe that's going to be alone. And then we're going to have to cross our charges to figure out what the new reaction or the new compound over here is going to be. It's going to be Na, and it's going to be Cl, because Cl is the other piece. And we've looked at this one enough that you're hopefully feeling pretty comfortable about that. Na and Cl make sodium chloride, aka NaCl. And then we go through and we balance. We have 3 Cl's, so we're going to need a 3 right here. It means you need a 3 right there. Put our ones, and we are balanced. Okay, going to our next example, we have Sn plus Mg3N2. So first we need to find Sn. Sn is tin. Tin is right down here. Mg is magnesium. Magnesium is right up here. So magnesium is more reactive than tin is. And we want the highest reactivity to not be alone. Highest reactivity should be in the compound. And that's already the case. Tin is not reactive enough to beat magnesium. This would be like if you're met the love of your life, or you're with someone who's really attractive and you like in every possible way, and then someone else just randomly on the street was like, hey, you want to leave that awesome person and date me instead? You'd probably be like, no, strange person, get away from me. I do not want to leave the person I'm with. So Sn is not good enough to kick out magnesium, which means for the first time this chapter, we have a no reaction. Rxn is just an abbreviation for reaction. You can write no reaction, you can write Rxn, but Rxn is the only thing that I will allow you to shorten it to. All right, So if this is the case, if the more reactive thing, because Mg is more reactive, that means there is no reaction. Notice in this case, Na was more reactive. So we'll go to the next one. Now we have Al. Al is a metal, so we're going to put it over here. And then we have HNO3, which is a little weird because H is not a metal. But if you actually look through on the chart, hydrogen is actually listed on the chart, even though it's a gas. So now we have to check. Hydrogen is right here. Aluminum is, let's see if we can find it. There it is. Aluminum is right there. So aluminum is more reactive. Currently, aluminum is alone. We do not want that to continue. Aluminum is more reactive. So it is going to boot out hydrogen, and it's going to give us AlNO3. Before we do that, though, hydrogen is now alone. We didn't have to ask up here because Fe was a metal, but hydrogen is a diatomic because it's a gas and it's on that little 7, so we've got to put a 2 there. Then we're going to have to figure out, you're going to have to cross your charges again. What is Al and NO3 combined together? Well, Al and NO3 are two pieces. Al has a positive 3 charge, you got to know that, and the NO3 is a polyatomic, so you got to know that is a 1-, meaning that our end result would be Al NO3 3 after we cross our charges. Then we go in and balance. This one I am going to be a little bit careful on. So we have a 2 here, and we could put a 2 here, but I'm going to write it smaller. We have 1 Al, we have 1 Al, we have 2 NO3s, and we have 3 NO3s, which means we're actually going to have to do 6 HNO3, 3 of those, 2 of those, and that means we're going to also have 2 ALs. To double check, 2, 6, 3, 2, can't all be simplified down, so we are good. Okay, for the next couple, I'm going to scoot my camera down a little bit so we can get our last few examples in there. You can get a good view of the floor in there as well. If I scoot it up a little, we'll get a little less of the floor. We have K plus H2O and Zn plus H2O. Now, on the reactivity series, there is actually a little box that is very important. Any metal below this line right here, this drawn in line below sodium, will not react with water. Lithium, rubidium, potassium, barium, strontium, calcium, sodium. All of those will react when placed into water, but anything below that line will not react with water. Even though water has hydrogen as its first element, only these guys are actually good enough to beat out H2O and make it turn into something and then H by itself. So if we check here, K is potassium. Potassium is above the line, so it will react with water. And this is where the other place in this chapter that people make their biggest mistake, which is K is going to boot out the H. But remember, water is actually HOH. So when water reacts with K, you're actually going to get the H by itself, which we just talked about as diatomic, plus now you're going to have KOH. K has a 1+ charge, OH has a 1- charge. We cross them, we don't need anything else. We get KOH. So when you split water, you have to split it as HOH, not H2 and O. You don't rip the H2 out and then make KO, potassium oxide. You would make potassium hydroxide whenever you mix them together. Now we got a balance. We have 1K, we have 1K, we have 3 H's, but they're spread out. So let's think of it instead as HOH. So we've got 2 H's by themselves, which means we'll need at least 2 of those. That means we need 2 OH's over here, which means we need 2 K's over here, which means we are balanced. 2, 2, 1, 2. For the next example, we have Zn plus H2O, and Zn is zinc. Zinc is right down here. Zinc is not above that line, which means if zinc is trying to react with water, it will just float in the water. There will be no RXN. Zn is unreactive in water. Some of the problems will ask for clarification. That's the only reason I'm writing these. You don't have to do that unless the question asks you why it is unreactive. Why is there no reaction? Because zinc is unreactive with water. Our final example, notice we have Cl2, and Cl is on this side. We're actually dealing with a halogen, and if that's the case, you're not going to swap with the first piece. Because Cl is negative, we want to swap it with the negative piece. In this case, that's Br. But not necessarily. We have to check. Cl is, in fact, above Br on our activity series. Cl is higher than bromine, which means it's going to kick out bromine. Bromine's going to be by itself, but it's diatomic, so it's going to be Br2. And then we're going to go plus, and we're going to draw a line. Now, Cr, if we check on the periodic table, does not have a consistent charge, but a nice, easy shortcut you can use on these. Cl and Br have the same charge. They're both -1. So if it took 3 Brs having a -1 charge, and Cl also has a -1 charge, then it's going to take 3 Cls for that one to be balanced. Then we can double check. We're going to have to do 2s here because we're going to have to do 3s here. We have 2 Cls, we have 3 Cls, we got to make that 6. We have 3 Brs, 2 Brs, we got to make them 6. So 3, 2, 3, 2 is how we're going to get that one balanced. All right. I know these can be a little bit weird, but if you have your activity series, they should be pretty straightforward. That's what I got for you today. If you have any questions, please shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.